Hello everyone, this is Roberto Torre-Ranz from the Deutsche Telekom Chair of Communication Networks, and today we are going to solve the second set of exercises about green mobile clouds, about energy and this kind of stuff for the cooperative communication system lectures. So we're going to start, if you remember from the lecture, normally in this set of exercises I do first talk a little bit about reminding a little bit what was this from mobile clouds, cooperative download strategies and so on. This time I'm not going to do it because you can just see the video again and that's it. So we are just going to go directly into the topic. Okay, so if we remember just slightly, okay, we have this cooperative download. Okay, we're going to have one node and different number of clients. This server is sending to these clients that are receiving in the cellular communication, and then we have some kind of short range communication here where in a time slotted channel one sends and the rest are receiving. This is how the cooperative download works, and then we have several parameters that we are going to use. So the power of the cellular to receive, the power of the cellular in the idle mode, the power in the short range to send, the power in the short range. Okay, there's a mistake in here. This is actually the power in the short range to send, the power in the short range to receive, and the power in the short range in idle, and then the rate, the data rate between the short range communication and the cellular communication. Okay, so let's see. Whoop. Let's read it first. A company is trying to reduce the energy of requesting a file to a server to a 40% of its original value, because they want to reduce the energy costs. So to do so, they decide to buy more devices and make them cooperate, because as we saw, the energy will be reduced. The engineer of the company gives the manager a report with three different possibilities. With four different possibilities where 4, 5, 6 or 7 devices are cooperating. So which one is the optimal, which percentage would be consumed in the cellular network, and which percentage in the short range network. So first we need to calculate the energy consumed for the determined number of clients in this sequential local exchange. Okay, so the energy, of course, it is going to be depending on the cell on the power when there is only one client, and the time when it's one client. Okay, so this is for a standalone user. This E over. Okay, so this is exactly what we have right now. What we have right now is one user, and it's getting the power of the cell and the time. If there are more users, then of course this will change. So what is the energy in the cooperation? Okay, so we have the time it takes in the cellular only, okay, and then also the power to receive from the cellular. The time it takes to the cellular, if we have, for example, 4 clients, so J here, J is the number of clients, the number of servers that we will have. So if we have 4 servers, we will have 1 divided by 4. So instead of sending in the cellular the file 100% of the file, we will send only 25%, so a fourth. And this is the time, is how it's going to be reduced. So 1 by J multiplied by the time if it was only one server, and of course then the power again to in the cellular power. Now this is going to be the energy consumption in the cellular. Now, what would happen in the short range? Let's go a little bit down again. So, in the short range communication, we will have a part to send and then a part to receive. And we know that Z is the range between the data rate in the short range and the data rate in the cellular. So the energy to send will be the time to send multiplied by the power to send. The power to send we know. The question is, what's going to be the time a user will be sending? Well, we know that the time it will take for this user to send that part, it's going to be in the cellular communication is going to be 1 divided by j multiplied by t sub c, which is the time it will take in the cellular to send that part. However, this time the short range is faster. So if it is 2 times faster, this means that it will take 2 times less for him to send this in the short range communication, and that's why this Z is contributing there. So in the end, the time to send this communication, this part of his data file, it's going to be 1 divided by Z and also by J. Okay, because the short range is faster. Now, what happens in the receiving part? If we go to the image here, we saw that for 4 users, we only send once and we receive 3 times. So we receive the number of users minus 1, because of course, so we need to receive the red part, the yellow part, and the green part. So in the end, the formula, the equation is exactly the same. So we also have the Z because the short range communication is faster than the cellular communication, and then we have J because we are only receiving a part of this whole this whole data file. But this time we are receiving only from J minus 1 users. And what we do is just we add everything. This is the energy for this sequential local exchange, because here I am giving these parameters about the idling, but there is no idle time in the sequential local exchange. Okay, so we just get these values. We have everything because yeah, we have everything. We have P sub C, we have P to send, we have P to receive, we have Z, and we don't have T sub C, but we don't need it. We will see that later. So we can just get for J equals 4, 5, 6, and 7, which is the report that the engineer gave, and we see that here we can reduce the energy by 0.55. Here by 0.48, here by 0.433, and here by 0.4, which is 40% of the total energy that we had, because now we can divide this here. Okay, we have here this T sub C, so we just divide it, and we get this this extra 40, this division of 40%. So in the end, for J equals 7, we will get a reduction of the energy consumption to 40% of the one that I was using before. Now, if we go to the what's going to be the energy, which percentage would be consumed of the energy is going to be at the cellular network and which one in the short range network. To do that, we come here and we see what is the energy in the cellular network, which is like 0.26, and then in percentage, which is 0.26 by oh, this is 0.4. Okay, I will change that. So this is going to be, it's not actually 54%, it's 0.26 divided by 0.4, which is 65%. And then in the short range is going to be 35%. 100 minus 35 minus 65 is going to be 35%. So let's go to the second exercise. 3 clients are cooperating to reduce the amount of energy and time used by the system to download a file. When 50% of the file is being downloaded, 2 more clients join the group. How long will it take for each of the 5 clients to download the file, and how much energy will they use? And let's assume that T sub C, so the time it's 1, so to download the file for a single user is 1. We already got the formula from the previous exercise. Important is here that there's no caching, there's nothing, so there will be only at 50, so we'll have 3 clients, the first 50% of the file, then we have 5 clients, another 50% of the file, and then of course these 2 clients need to download the other 50%, so at the end we will have another 2 clients with 50% of the file. So we have here 50% of the time would be T divided by 2, of course. So let's go to the first 3 clients. We get this formula, and we get T sub C divided by 2, which is the first time for the cellular network, for the sending in the short range and for the receiving in the short range. This with value j equals 3, and this with value j equals 5. And then of course this is the addition of both energies, so we see that the energy consumption is going to be 0.57 joules. Now if we go to the second two clients, it's more or less the same, but in the beginning we will have j equals 5 because we will have 5 clients. Then when this 50% of the file from the other 3 clients is finished, we will only have 2 clients. So in the end we add this up and we get that the energy consumption is 0.69 joules. Now regarding the time, let's scroll it a bit down. Let's just go here. So we have that the time of cooperation is going to be 1 divided by j multiplied by the time it takes for one single user, so time standalone, and then of course the number of users, because this j in the end is j minus 1, that is the contribution in the part from receiving, plus 1, which is the contribution of the time of sending. So in the end it's j divided by j plus by jz, so it's only 1 divided by z, as you can see here at the right of the equation. This would be of course the cellular time plus the short range time. And again we do this exactly the same for the same operation with T sub C divided by 2. Okay, so for the first 3 clients we have this equation, as you can see here. We have 1 divided by 2j multiplied by T sub C plus 1 divided by 2z multiplied by T sub C. And then we substitute with value j equals 3. And here exactly the same with value j equals 5. We add everything up and we see that the time it is 0.466 seconds to download the file. Then for the second 2 clients is exactly the same. Okay, so you can see here, I will drink a little bit of water, if you excuse me. Good. So for the second 2 clients is exactly the same. Okay. We have for j equals 5, it's actually exactly the same, 0.2, and then for j equals 2 is a little bit more. So in the end, the time it takes for the two second clients to download the file is 0.55 seconds. Good. Now let's go to the cooperative download with PLE. In this case, we see that the users have 2 antennas. One is going to be the cellular antenna and the other one is going to be the short range antenna, and they can do both at the same time. So they can do this local exchange, this short range exchange, and at the same time they can still be receiving, as you can see here. So we have this, we are sending, and then we have also this here, that means that we are sending and receiving in the short range and at the same time we are receiving the chunks of the next part of the video or of the file. So what we're going to do first is to formulate the energy equation for a cooperative download scenario with parallel local exchange where the number of clients of cooperating J is bigger than the ratio between the short-range data rate and the cellular data rate. Then we get the energy for 6 clients and the value of the table if the time and the values of the table if the time to download the file for a single user is 1 minute. And get also the energy for 4 clients as well. Okay, so let's start with the formulation of the energy equation. The first thing we need to see is that if J, so if the number of users, I mean, let's look at this picture. Okay, so the data rate, which means for in our example is 5, right? This means that the short range will be this width of these chunks will be 5 times faster than this one here. This means that we can put 5 of these chunks, 1, 2, 3, 4, and 5 in the time it will take to receive 1 chunk of the cellular. However, we only have 4 clients, which means that we have here some spare time that we are not receiving anything, we are not sending anything. That means that the antenna is in idle. However, if we have too many users, this means that these chunks will be actually longer. And the interface that's going to wait is the cellular interface. And we will have the cellular interface in idle mode. This is mainly this is the most important comparison between the rate of the number of clients cooperating and the data rate. So in our example, J, the number of clients cooperating, is bigger than the ratio between the short range and the data rate. Here we can see, okay? So that means that the idle it's going to be where? In the cellular networks, because too many clients are cooperating. Okay? So we also have that 1 divided by J, I mean this is just basic mathematics, is less than Y divided by Z. What's going to be the energy in the cellular when receiving? This is exactly the same. J is going to be the number of users, so we have 1 divided by J multiplied by C multiplied by the power consumed on the cellular rate to receive. Now the time divided by the number of clients. Now what's going to be the part that we are going to be waiting in the cellular phase? Because as we said, we have more users than the data rate ratio, which means that the cellular part is going to be in idle. Well, we have this is 1 divided by J is the number, is the energy consumed when we are sending, so this would be exactly this chunk here. Okay, so we need to calculate what's going to be the time from this point until until more or less would be around here. So the point to receive from the short range, and if we subtract those two values, we will see what is the difference in time where the cellular antenna will be in idle. And this is what we do. So 1 divided by Z, oh, that I cannot do. 1 divided by Z is multiplied by T sub C is the amount of time it takes for one chunk to be sent and received in the short range communication, and 1 divided by J is the time multiplied by T sub C is the time of one chunk to be received in the cellular communication. If we subtract these two, we will get the time it will be in idle. And then of course if we multiply it by the power to be idle, we will get the energy. So with this we have the contribution of the cellular network. We have the contribution of the cellular while receiving and the contribution of the cellular while being in idle. Now let's see what's going to be the contribution of the short-range communication. In here we will always be, because the short-range communication is slower than, as you can see here, this slow, it will be slower than the cellular network, which means that we are not going to have idle time here. We'll just have time to receive and to send. So we can just put it here. Okay, so what we see now is it is exactly the same as what we saw in the first exercise. So in the first exercises, so the time to receive it will be less than the time to send chunks in the short range, and so we multiply the time to send by the power to send, which is I mean, if this is familiar to you, it is going to be 1 divided by jz multiplied by the time in the standalone version, and then by the power to transmit in short range, because if you remember, to transmit we only transmit our part. This is exactly the same. Let's go to the image. We are only transmitting, we are only sending here once. Then to receive, however, we receive from all the clients -1, because of course we are not sending to ourselves. So this is going to be the contribution. Okay, and then as I said, there is not any kind of idle, because the idle is in the cellular. So when the bottleneck is in the short range. And you can see here there is no idle time because the number of users is bigger than the ratio in the data rate between cellular and short, between short range and cellular. So we add everything up. So we add the contribution on the receiving in the cellular, the contribution on the idle in the cellular, the contribution on transmitting in the short range, the contribution on receiving on the short range, and the contribution, which is 0, on idling in the short range, and we get 26,2 joules. That would be it. Now we do the same, but for 4 clients, and this is a trick question. Of course, I will not just make you do exactly the same, but by changing the numbers, and that's it. Because for 4 clients, the thing is that the set is 5. So for 6 clients, J was bigger than Z. But for 4 clients, J is smaller than Z, which means that we will not have idle time in the cellular anymore, but we will have idle time in the short range communication, and we need to calculate this again. We are now in a fast short range technology, which means that this is exactly the same, but this time we are not going to have this contribution. This contribution, it's going to be 0, because there is no idle in the cellular communication. This contribution stays the same, as well as this contribution, the short range to send and the short range to receive. But this time we have some idle time in the short range communication. And this is also what we need to take into account. So now we have, before we had 1 divided by Z minus 1 divided by J, because of course 1 divided by Z was the number of users, which was bigger than 1 divided by J, which was the time it takes to download the chunk from the cellular. But this time 1 divided by J is bigger. Because it's the time it takes from the cellular, and 1 divided by Z is the time it takes of this chunk to be disseminated to the rest of the users. So we subtract 1 divided by J minus 1 divided by Z. If I had a board here, it would be way easier to explain, but here, as you can see in the picture, 1 divided here, for example, this is the example that we have, where we have a fast fast short-range communication, because we have 4 clients and it looks like we can fit 5. Okay, and this is exactly this idle time that I'm talking about. This would be until the green chunk. This would be 1 divided by j multiplied by t sub c, and if until this dotted line, this would be 1 divided by z. No, sorry, I said it wrong. This would be this until the dotted line would be 1 divided by j, and until the red chunk, the green chunk would be 1 divided by z. Exactly. So where are we? Okay, here. Yes. Okay. So it's important, just be aware of this, okay? So it depends on the ratio of z and j. You will need to see if it's one or the other one that we are looking at. So now, in terms of time, what would be the best scenario so the clients do not have to wait anything for the file? And if this scenario will be the best in terms of energy. Why and why not? So, if z is equal to j, there will be no idle time. That is the idea, right? So if because the idle time it comes because of the difference in time of sending in the of receiving in the cellular network, and also sending and receiving in the short range network. So if z is equal to j, as I said, there will be no idle time. So this means that the idle in both of them is 0. Of course, t sub c makes no sense because this will mean that. But I'm going to explain how to get to this, because if you just say this, okay, it's good, but we need to prove it, of course. So if t sub c is 0, this means that the time it takes to download the file is 0. Makes no sense. If the power is 0, it also makes no sense, because the power, in idle, but in idle it could be 0 if you just turn it off, but you don't turn it off the antenna unless you know you're not going to use it long. So it also makes no sense that the power being in idle is 0. So the only term that can be 0 is this one. Okay, and here's how we get that. Of course, j needs to be exactly the same as z. We can take this value, or we can take the other one. This one I took the one in the short range, but it doesn't matter. So regarding the energy, so we saw that for z equals 5 and different j's, the energy changes, of course. Now let's see what happens when z is equals to j. We get this, okay. We just need to, it doesn't matter, so we just need to put here the same j and the same z. So this would be like z squared, j squared, z squared, j squared. We can test it, for example, for j equals 5, j equals 6, or something like this. In this case, since we had z was equals to 5, we are just going to make exactly the same with j. So j is going to be equals z, so it's going to be 5. So for j and z 5, we get that the energy is going to be 28.8, which is higher than for j equals 6. If we go scroll up, we see that this is 26.2, and this one is 28.8. So no, the best solution in terms of energy is not the best solution in terms of idling time. Okay, so let's now go to the third exercise. If the power consumed in the short-range communication is double the power consumed in the cellular communication, would it be a good idea to cooperate if the clients want to save energy in the download parallel local exchange scenario? Why? Then assume that the transmitting energy is the same as the receiving energy, and the number of clients is equal to the difference in the data rate between the cellular network and the short-range network. Okay, so we had exactly the same, the equation for one client, which is T sub C multiplied by P sub C. Okay, and now we have multiple clients. So we have the energy in the parallel local exchange for cooperation when J is bigger than 1. This already calculated, of course. We were assuming that J is equals to Z, so this means that this idle time is going to be 0 and this idle time is also going to be 0. And then so this energy in the parallel local exchange for cooperation is going to be exactly the formula that you can see here, only with the contribution of the cellular reception, the contribution of the sending, and the reception on the short range. Now, of course, we can substitute Z for J or J for Z, doesn't matter, and then the power in the short range is going to be the double of the power in C. Think oh, hold on a minute. Yeah. So we substitute here. Okay. So here we had Z. Now we have J square, and this is how I mean, it's pretty straightforward. Okay. So if we go to the ratio, we got the power in the local exchange, in the parallel local exchange of incorporation, divided by the power in the over. So for one single client, and this is the ratio that we get. Okay, we can make it a little bit bigger. Here you can see, I mean, we can just continue a little bit, expand it, and so on. 2 minus 2, and in the end we get, if you see, this would be J plus J, 3J plus 2 minus 2 is 0, so it will be 3J divided by J squared, which is 3 divided by J. So, would it be a good idea to cooperate, now that we have the rate, would it be a good idea to cooperate if the clients want to save energy? Well, so if J is 2 or 3, then there will be no gain. But if J is bigger than 3, there's going to be J gain. So if we have more than 3 users, 3 clients cooperating, there is going to be a gain. Okay, this is the exercise mainly. Okay, now we go to streaming. In streaming, if you remember, we don't have the chunks saved in anywhere, so it's always going to be sending this part, and we are going to send it only to one of the clients, and then with the local exchange they will exchange their part also sequentially, because there's no other way. So here, 2 football-addicted friends were watching the first Germany match of the Russia 2018 World Cup against Mexico. They are worried because they watched the streamed football match and it takes too much time for the signal to arrive to the receiver. They wanted to see it earlier. To improve that, in the next matches until the final, because of course Germany will reach it, of course this will do it from 2 years, so sorry. The first one claims that they should buy another 3 receivers and connect them to the streamed match, making all 4 devices to cooperate with each other so the signal will be faster. The second one says this is a nonsense because it will not help and they will throw away their money. Who is right in this discussion and why? Well, here, I mean, this is a lot of wording, but the actual question is if cooperation in streaming will help to deliver the content faster, to make this time to download the stream smaller. And as you can see here in the picture, it is quite straightforward. Okay, here we receive one chunk, and the rest are going to. So here will be the point where the first user can receive the chunk, and this one would be the point where the rest receive the chunk. But since we cannot store the whole file anywhere, we cannot send it to multiple places, and we will not be able to save time. Okay. So streaming is done live, as I'm saying, which means that the time cannot be reduced. We cannot reduce the time that it takes by doing cooperation. Adding more devices will reduce the energy consumed. However, the time will never change, because we are not downloading, but watching this game while this is being streamed. Therefore, there is no point in buying new devices. So the second friend, is right in this discussion. And that's it regarding the exercises. So I will upload this file also to Opal, so you can have it. If you have any questions regarding the exercises, again, you can write me a mail, ask me about whatever you need, and yeah. I hope it's clear, and I thank you for watching.